Welcome students to our video notes lesson on section 1.4 part 2, where in this section we go ahead and take a look at continuity. What does it mean for a function to be continuous? What do points of discontinuity look like? And what are some properties of continuity? Okay, so let's just get started right away with what does it mean? What is the formal definition for continuity at a single point? So this is a point on a function, and this is what has to be true. So there's three things that have to be true to be able to say f of x is continuous at that point where x is equal to c. So c is kind of representing one specific x value. Okay, so the first condition is that f of c has to exist. Okay, so what does that mean, f of c exists? Well, let's look at these first two images here. So in the first picture here, here's where x is c. If you go down to the function, there is a solid dot there where f of c would be. So this is what it means for f of c to exist, is that there's a solid dot on the function where x is c. Over here, we can see here's x equals c, and there's this hole. That means there is no y value that we could call f of c. F of c does not exist. So that means there's a hole in the graph. Okay, so for f of c to exist means no holes. All right, now, second condition is that the limit as x approaches c from both sides also has to exist. So remember, from our last lesson, we learned that if there's no plus or minus here after the c, that means that this is referring to a two-sided limit. So the limit from the left and the right have to be the same. Looking at this first picture here, so here I have, this is where my c value is, right, this section of the graph. And I can see that as x approaches c from the right and from the left, both of those parts of the function are approaching the same limit value. So I can see here that the limit as x approaches c on this function definitely exists. But if you look at this point c, so we're choosing a different point c on the same graph, this one here, I can see that the limit from the left looks like it's around 2, whereas the limit from the right is 1. So the left-hand limit exists and the right-hand limit exists, but they don't equal each other, which means that the two-sided limit does not exist. Okay, so what does it mean for the two-sided limit to not exist? That means we've got ourselves a jump on the graph. The left side is not coming together to meet up with the right side. So there's a jump in our graph. So we don't want any jumps. No holes, no jumps. Okay, now this third one is maybe not as obvious as the first two. So I want you to put a star by it and indicate to yourself in your notes that this is the part you're going to have to work on remembering. You're going to have to remind yourself of this and study this before our quizzes and tests. Okay, so this one says that the limit as x approaches c has to also equal the y value of f of c. This is important. So let's kind of take a look at what this is talking about. So here we have two more images to compare and contrast. So here is a function, and here's my x value of c. So if you look at the graph here, you notice, okay, there's a dot, it's filled in, so there's no holes, so condition 1 is met, right? We have f of c exists. Condition 1 is met. We can also see that the limit from the right-hand side is equal to the limit from the left-hand side. They're coming together to the same value. So the limit as x approaches c of f of x also exists. Check. We can also see that where that left-hand side and right-hand side are coming together is at this point f of c. So f of c is like right here. And that also is what the limit of the function is. That's what f of x is approaching as x approaches c from the right and left. So we could say that the limit as x approaches c of the function happens to equal that y value right here of f of c. Okay, so let's take a look at this one on the right. So we can see that condition 1 is met because there's a filled in dot up here. So here's where x is c, right? There's a filled in dot right there. So that right there would be my value for f of c. This is the y value that f of x equals when x is c, is up here where the dot is filled in. So condition 1 is met. F of c exists. I can also see that as x approaches c from the left and right, here and there, the two sides are wanting to come together to this one particular value right here, right? That would be my limit as x approaches c from both sides. So my limit as x approaches c also exists. The left-hand side and the right-hand side are coming together to the same value. But these are not equal to each other. The limit as x approaches c does not equal f of c. It equals some other y value down here. So we would say that f of x is not continuous right here at this point c because that third condition is not met. So it's perhaps the less obvious condition, but is necessary in order for a function to be continuous. So of all these images we've shown you here, the two that are continuous at all of their different points are this one and this one. So to be continuous, we want to make sure there's no holes, right? No point where f of c wouldn't exist or maybe wouldn't equal the limit as x approaches c. We don't want any jumps like this here. We don't want any places where that limit won't exist. And we don't want any kind of random hole / solid dot somewhere else because that means the third condition is not being met. All right, so let's go down here. So this is talking about, let me actually back up. So this is when I'm looking at continuity at just one single point, just one part of the function. We're just looking to see if it meets these three conditions at that one point. But we can also say that a function is continuous on an open interval if it's continuous at each point on that interval. So if these conditions up here, f of c exists, limit equals f of c, if those three conditions are met for every single point on an interval, we can then say, okay, on this interval, so let's just use a and b as our left and right hand endpoints, we can see for every single point in between them, so I could put a c here, or I could put a c there, or I could put a c there, at any one of these points, those three conditions of continuity that we talked about above are met. So this function would be considered continuous along that interval. I don't need to worry about what's happening at the endpoint. I don't need to worry about these holes because I'm not saying it's continuous from A to B. I'm saying it's continuous on the open interval. That means we're excluding the endpoints between A and B. Everything in between there is good to go. Whereas over here, I could say the function's continuous from A to C, or I could say it's continuous from C to B, but because there's this one spot right here, we have a jump right here, a spot where the limit as x approaches c from the left does not equal the limit as x approaches c from the right. So then the two-sided limit doesn't exist. So condition number 2 is not met. So because f of x is not continuous at x equals c, and c is between a and b, then we could not say that it's continuous on the open interval. But I do want to say, we could say this. We could say that f of x is continuous from A to C, open interval, or from C to B. It's continuous here separately and there separately, but not all the way through because of the jump. So that's continuity on an open interval. We ignore the endpoints. We could also say that f is continuous on a closed interval, which we indicate with the brackets. If f is continuous at each point on the open interval, like we looked at above, and if f of A exists and f of B exists. So in other words, we have closed circles on our endpoint, so no open circles. So if f of A exists and f of B exists, and f of x is continuous for every point C between A and B, right? Here's an example of one. Then the function we could say is continuous on this closed interval. And here's kind of a picture of what that would look like. Okay, so sometimes we like to think of functions that are continuous everywhere. What does that mean, everywhere continuous function? That means a function that is continuous across the entire real number line. So from the infinite left to the infinite right, from negative infinity to positive infinity. So what that basically means, like what the informal understanding of continuity means, we could trace its entire graph without lifting our pencil off the page. That's sort of the informal idea of continuity. We can think of this word connected. So when you think continuous, we think connected. And if a function is continuous everywhere, you can trace its entire graph without lifting your pencil off the page. So these are just kind of some examples of that. There's no holes, right? There are no jumps and no endpoints. There's arrows on the end, right? So the functions just keep going, and they're all connected and smooth. F of c exists everywhere, the limits exist everywhere, and the limits always equal f of c. All right, so that is a function continuous everywhere. So naturally, when studying continuity, we're going to take a look at discontinuity as well. What does it look like when a function is not continuous at x equals c? And the word we use to describe that is we say the function has a discontinuity at this point c. So it's when any one of the three definitions of continuity aren't being met. So here, if we look at, this is function g, this is function f. So we would say that g is continuous on the open interval from a to b, right? A and b are not, g of a does not exist, g of b does not exist, so we cannot include the endpoints, but it is continuous everywhere in between. Whereas function f over here, there's this point, c, between a and b, where the limit as x approaches c of this function does not exist. So that's condition number 2 is not being met, right? Condition 1 is met because it exists there. Actually, conditions 2 and 3 are not being met because the limit doesn't exist. So there's a point on this interval where we would say the function is not continuous. F of x, we could say, is not continuous at x equals c. Or we could say f of x has a discontinuity at x equals c. Okay, so now we get into the meat and potatoes of this lesson, is classifying the different types of discontinuities, because we're going to want you to be able to identify where a function has a point of discontinuity and what type of discontinuity it is and why. So there's two main types. There's the removable discontinuities, which I'll talk about in a second. There's also the second type, which is non-removable. So we break discontinuities into these two categories, removable and non-removable. Let's start with removable. Okay, so a removable discontinuity, this is important. This is when the two-sided limit exists. Okay, so that means we have the left-hand limit equal to the right-hand limit, but either f of c doesn't exist, so condition 1 isn't met, or the limit as x approaches c does not equal f of c. So this is where condition number 2 is met, but either condition 1 or 3 is not. Okay, another way you can think of this would be a hole. So these are when you're dealing with holes in your graph, because your limit exists, but either they're coming together at a point that doesn't exist, or they're coming together at a point away from or different from the place where the function does exist. So it's important that we begin to look at what types of functions would be the culprits. What kind of function would create this kind of thing in a graph? So I want you to remember these. So rational functions. These are functions that have fractions, right? Where you have a polynomial function in the numerator and then another polynomial function in the denominator. The exact place of the discontinuity will happen when the denominator equals 0. So in this case, the denominator is x plus 1. So the denominator equals 0 when x is negative 1. So if you look over here at our graph, we can see that it's right at that x value where I have a hole in my function. That means f of negative 1 does not exist. There is no value for it. But the limit exists because if I factor the numerator, so I can take this equation and factor it into x plus 3 times x plus 1 in the numerator. And so because there is this common factor that reduces or removes the factor in the denominator, cancels it out, right? And I end up with this expression just equaling x plus 3, that means the limit of this exists as x approaches negative 1. The limit as x approaches negative 1 of x plus 3 would just be 2. So you can see that's where the function on the right-hand side is approaching, and on the left-hand side, they're both approaching 2. But if I try to plug negative 1 into this original expression here for f, I just try to substitute it in, I get negative 1 squared plus 4 times negative 1 plus 3 all over negative 1 plus 1. So I end up with 0 over 0, which is undefined, right? We call that indeterminate form. So no actual y value when x is negative 1, but a limit value when x is negative 1, which is equal to 2. So this is what it means for a function to have a removable discontinuity. You can also think of it as when you have a rational function with a common factor in the numerator and denominator. This, like the discontinuity, gets removed, right, from the fraction. So rational functions are one main cause of these holes or these removable discontinuities. Another type of function that can also create a removable discontinuity or a hole in your graph would be a piecewise function. Now, this doesn't mean that every piecewise function has a hole. It's just you always want to check. You should always check and see if maybe there is one. So I just first I look over here and just kind of make sure that f of x exists everywhere. First, like just to see, is there anything left out of the domain? And I noticed that there was never an equal sign on either of these inequalities. So that means f of 2 does not exist, right? So you always want to check if that's the case. But you also should check if the left side of this function is equal to the right side. So I would want to take the 2 and plug it in for x in here, and then take the 2 and plug it in for x into the other one, and just see if those two sides are equal. So here I get 4 minus 3 is 1, 4 minus 3 is 1. So this could potentially trick you into thinking, oh, we're all good, the left side equals the right side, which it does. So what this is telling me is that the limit as x approaches 2 of f of x does exist, right? The left-hand limit is equal to the right-hand limit. So condition 2 is met. It's condition 1 that's not being met. So what does that look like on the picture? Well, over here you can see this is the part of the graph that was the x squared minus 3, right? The parabola part of the graph where x was less than 2. So this is happening to the left of 2. To the right of 2, you can see I've got this linear function, right? This guy here is the 2x minus 3, and that's happening to the right of 2. And they both equal 1 when x is 2, so that's right here. The problem is I was not allowed to include 2 in either of these pieces, so that left a hole in the graph, which is basically a removable discontinuity. So just always check these things. Check to make sure the left equals the right, because if not, that would be a jump. And check to make sure if there's any part left out of your domain which would cause a place for f of x to not exist. So that brings us to non-removable discontinuities. These are the type where your two-sided limit does not exist. So that's kind of the main difference between removable and non-removable. In a removable discontinuity, your two-sided limit exists. In a non-removable discontinuity, it doesn't. That's the main difference. So f of c may or may not exist in these scenarios. So you may have a hole also, but the point is that the left side is not equaling the right side. So we have what's called a jump discontinuity. Or actually there's two types. So within this second form of discontinuity, which is non-removable, where the two-sided limit does not exist, you have a situation where either you have a jump discontinuity, where the left and right-hand limits separately exist, but don't equal each other. So you have this thing called a jump discontinuity. That's type 1 of a non-removable. Type 2 of a non-removable, let me come down here, is called an infinite discontinuity. And that's where either one or both of your one-sided limits, so either your left-hand limit or your right-hand limit or both, end up approaching infinity. So we would say technically those limits don't exist on one hand, right? Because they're increasing or decreasing without bound. So you have something either going like that, right? Or like that, Or maybe that's happening on both sides. But at any rate, it's not a finite limit. So it's not just a jump, it's a full-blown vertical asymptote, right? So that's another type of non-removable discontinuity. But let's go back to the jumps for a second. So again, a jump discontinuity is a non-removable discontinuity because the two-sided limit doesn't exist, but it's not as extreme as a vertical asymptote because the left and right hand limits exist. And when I say that, I mean are equal to finite values. They're just not the same value, right? They're just not equal to each other. So you have something that looks like this picture down here, a jump in your graph. Okay, so what types of functions would be considered those culprits? What types of functions should you be on the lookout for functions that cause jumps? So piecewise comes up again. And so again, this doesn't mean that all piecewise functions have jumps. It just means that you always want to check. You should always check. First, we look here at our domain and say, okay, is every x value included? And I can see that yes. So the domain is equal to all real numbers. So there's no point where f of x doesn't exist. But then you want to check your two sides and see if they are coming together to equal the same value at the x value where the function changes from one piece to the next. So the x value where that happens is at x equals 1. And on the left side, right, where x is less than 1, so I could say that my left-hand limit would equal 4, right? My left-hand limit as x approaches 1. And then my right-hand limit as x approaches 1, I have to plug 1 in here to see, but it looks like it equals 2. So my limits exist, right? They're not going off to infinity or negative infinity. They're equal to finite numbers, but they're not the same finite number, right? The left-hand limit does not equal the right-hand limit. So you have something like this. On the left-hand side, we're at 4, and on the right-hand side, we're down at 2. And as you can see, there is a hole here, but this is considered non-removable, right? Because the two-sided limit does not exist. So we don't call it a hole, we call it a jump discontinuity. The left side is not equal to the right side. Another major culprit of jumps, we talked about this in our part 1 video, is the greatest integer function. The function with this equation here, where the y value is equal to the greatest integer that is less than or equal to the x value. So because the y value is always an integer, we have a jump at every whole number for x. At every integer, we have these jumps where the y value is finally able to go up to the next integer, right? So this function will always have jumps. It'll always have places where the left-hand limit does not equal the right-hand limit. So you just want to figure out where those jumps are happening. For the parent function, they're happening at all the whole numbers, at all the integers. And then a third culprit for jumps, right, places where the left-hand limit doesn't equal the right-hand limit, is that unique function that we looked at in our part 1 video, where you have the parent function that has the absolute value of x divided by x, some kind of variation of that. So this is just a variation of that. So this function always has a graph that looks like this. It has one step that's up at +1 and then another step that's down at -1. And the jump will happen at the value of x that makes the denominator 0. So it's when that denominator is equal to 0, which in this case is x plus 1, which in this case is -1. So that's why this jump, where it goes from equaling +1 to equaling -1, happens when x is equal to -1. So when you see a function in this format, where the top or bottom, because this could also have looked like this. They have the same graph. Where one of the pieces, so the pieces have to be the same, right? It has to be x plus 1 and x plus 1, right? To follow this parent style. Same thing inside the absolute value, that's outside the absolute value. They're being divided by each other, which is why they always end up canceling to 1, but one of them stays positive when the other one can change negative, is what's happening. So whenever you see something like that, remember it'll have a jump, it'll have a place where the limit doesn't exist, which in this case is at -1, which means it's not continuous there. And it's a jump discontinuity. Okay, moving on to type 2. Remember, this is type 2 of what we call non-removable discontinuities. We think of these as infinite discontinuities, but I want you to think of them as vertical asymptotes, because that's what they are. So anywhere a function has a vertical asymptote, that is considered to be a non-removable discontinuity, and it's more extreme than a jump. It's an infinite discontinuity because either one or both of those one-sided limits are approaching infinity. Okay, so what kind of functions should we be on the lookout for? Well, basically any function that has a vertical asymptote. So we've got rational functions, which I had mentioned earlier because they have factors in the denominator that equal 0. And then certain trig functions, specifically tangent, cotangent, secant, and cosecant. Those are the 4 trig functions that all have vertical asymptotes. And then, of course, logarithmic functions have vertical asymptotes. So we got to be on the lookout for all those functions because anytime a function has a vertical asymptote, it has a discontinuity there, specifically a non-removable or infinite discontinuity. So here's an example here. We've got secant of pi x. So I know, okay, this is secant, so I know it's going to have vertical asymptotes. So I need to figure out where this function will have the vertical asymptote so that I know where it's not continuous. So I could say it's not continuous at here, here, and here. Well, okay, so first I have to think about the parent function, or this is what I want you to do, y equals secant of x. And I want you to think, okay, that's the function that had vertical asymptotes at all of the pi over 2's. Because those are the places where cosine was 0. Right? So that's the parent function. It has the vertical asymptotes anytime cosine is 0. So all the pi over 2, all the odd pi over 2's. Okay, but this one is secant of pi x, right? So then I want you to remember, well, the period of the function will change based on that number, that coefficient of x inside the function. So the normal period for secant is 2 pi. The function repeats its same cycle every 2 pi radians. So I take that original period and divide it by this coefficient of pi that was being multiplied to x, and I get 2. So that means this function will repeat its cycle every 2 radians. So instead of having asymptotes at all the pi over 2's, right, it'll be at all the halves, basically. So it'll be here at 3 halves, here at 1 half, 1 half, 3 halves, 5 halves, etc. Because the cycle repeats every 2 radians, so it'll have an asymptote at all of the odd halves. So if we were asked to say, where does this function have points of discontinuity, we could say, well, it'll have a discontinuity at any, where x is equal to n over 2, where n is any odd integer. So 1 half, 3 halves, 5 halves, etc. Right? At any of those points, we know that our secant of pi x, which has a period of 2, will have an asymptote at any one of those values, a vertical asymptote, which is a non-removable discontinuity. So quick recap on discontinuities. So I want you to be on the lookout for zeros in the denominator because they either create wholes or vertical asymptotes. Piecewise functions because they could possibly have things left out of the domain, or the pieces may not connect. Greatest integer function because it always has jumps. This unique function here because it always has one jump, and that would be when the denominator equals 0, and any other function with a vertical asymptote, so trig or logs. Okay, so here's kind of the wording the book will give you. It'll say, find the x values, if any, at which f is not continuous. So we're looking for points of discontinuity, right? We're looking for wholes, jumps, or vertical asymptote. It'll ask us to classify as either removable or non-removable. So we need to remember removable is when the limit exists, right? So we need to kind of pay attention to that. Non-removable is when the limit either goes off to infinity or doesn't exist, right? Jump or vertical asymptote. Then we describe the intervals on which the function is continuous. So basically it'd be everywhere other than the points where it's not continuous. So this is just questions I want you to kind of be thinking about in your head, but this is not how I want you to answer the question. So I want you to say, okay, any values that make f of x undefined? Well, this is rational, right? This is a rational function, so we know that f of x will be undefined when the denominator is 0. So I know that x minus 6, when that's 0, which is at 6, that's a point where f of x is undefined, right? So what x value is 6. That's definitely going to be a non-removable because this factor here of x minus 6 does not cancel with any factor in the numerator. This factor is remaining in the denominator, and that is because the limit as x approaches 6 for this function doesn't exist, right? I can't, if I plug 6 in here, I get 4 over 0. We're going to be looking in the next section that actually creates infinite limits on left and right. But we know right now it just doesn't exist. The two-sided limit for sure doesn't exist. So this is definitely non-removable. You can also remember this is a rational function where a rational function has a 0 in the denominator, which is at x equals 6. That's where its vertical asymptotes are. So this function basically has a vertical asymptote, right? It looks like this. So there's kind of like this. Here's x equals 6. There's like this dashed vertical line. The left side of the function is shooting up to positive infinity. The right side's going down to negative infinity. It's a vertical asymptote. Infinite discontinuity. So what I want you to do is say, okay, based on having kind of thought about all this in your head, this is how you'll answer. So you will say f of x, because it asks you to specify, right, whether or not it's removable or non-removable. So then you'll say f of x has a non-removable discontinuity at x equals 6 because the limit as x approaches 6 of this equation does not exist. And then it's continuous everywhere else though. So f of x is continuous on the interval starting from negative infinity up until 6, right, with a parenthesis because we're not including, and then also from 6 to positive infinity. So those are the open intervals, right, where the function is continuous. So like this piece that goes from negative infinity up to 6, right, that part of the graph, continuous. And then I skip over 6, and then this part of the graph that goes from 6 to positive infinity is also continuous. So these two sections separately are continuous, but at x equals 6, the function definitely has a non-removable discontinuity. So here's part B of the same example. So same instructions. We're given this function. We're supposed to figure out if there's any places where the function is not continuous and then describe the intervals where it is. So that gives us a trig function. So we need to remember, okay, I remember tangent has vertical asymptotes. Those are places where it's undefined, and it's definitely, those are non-removable discontinuities. So now we just have to figure out at what values of x does tangent have its vertical asymptote. So you can either just remember the parent function for tangent. You could also remember that tangent is sine over cosine, so it's going to be anywhere that the denominator or cosine equals 0. And that is at all of the odd pi over 2's. Pi over 2, 3 pi over 2, 5 pi over 2, etc. You can see that in the graph here. So these are all of the sort of pi over 2 marks. It's pi over 2, 3 pi over 2, etc. Our answer would be, well, f of x, which is tan, has non-removable discontinuities, vertical asymptotes, at x equals, and then we could say something like this, pi over 2 plus pi k. So k is any integer. Because basically if you take a pi over 2 and you add pi to it, or 2 pi over 2 is the same thing, you get 3 pi over 2. And then if I add another 2 pi over 2 to that, I get 5 pi over 2, etc. So pi over 2 plus pi k takes care of all of these sort of odd pi over 2's. So this is the place where tan has non-removable discontinuities. And then you could say tangent is continuous on, and so for this one, you could maybe do something like this. Well, we know it's continuous from negative pi over 2 to pi over 2, and then it's continuous again from pi over 2 to 3 pi over 2. So basically between all of your pi over 2's it's continuous. And so you can kind of see a pattern. So then you can just say dot, dot, dot on the right and dot, dot, dot on the left. So it's going to be basically all of the places of the function in between all those pi over 2s. See, there's no holes or anything for these parts of the graph. So each one of these tangent cycles is continuous until it hits an asymptote, and then it's not continuous at the asymptote. Okay, so why don't you go ahead and try some yourself. Okay, so for the you try, for part A, this is kind of the scratch work I want you to go through, where you notice it's a rational function, so you want to see if there's any common factors between numerator and denominator. So we'd have to factor the denominator and see that the two factors would be x minus 2 and x plus 1. So that's where we would notice, okay, there is this removable discontinuity when x is 2, because at that point, if I plugged in 2 for x, I'd have 0 over 0, and I've canceled that out. So this would create like a hole on your graph. It would also create a point where the limit for both sides of this equation when x approaches 2 exists. So the limit exists, but the function does not at x equals 2. Then you might notice that there's still a remaining factor of x plus 1 in the denominator, so that means that this would simplify to equal 1 over x plus 1. And this remaining part of the function would be undefined when x is negative 1. And the limit would not exist to the left or right because the values would be going off to either positive or negative infinity. So this function has also a non-removable discontinuity when x is negative 1. So the short way of thinking about it is just whatever factors cancel between numerator and denominator, that's a removable discontinuity or a hole on the graph. And then whatever factor remains in the denominator after you've simplified the expression, that's going to be your vertical asymptote, which is your non-removable discontinuity. So that's just kind of the work that you do, but this is how you would answer the question. You would say f of x is continuous on these intervals. So you kind of go from negative infinity to infinity, but split it up at the negative 1 and the 2 marks. And then you would just say at x equals 2, there's a removable discontinuity, and at x equals negative 1, there's a non-removable discontinuity. Okay, then for part B, what I would want you to remember is that this is the notation for the greatest integer function. This is the function that has steps all along with jumps at every integer. This one has a plus 4 on the inside, so the function has shifted to the left 4 units. But that doesn't change the fact that the function will still jump at every whole number. So it just starts over here at negative 4 as opposed to 0. But you can see here and here and here, the jumps are still happening at integers, at integer values, and they will continue to happen at all integer values. So that's kind of the thinking that you do behind it. But then here's the answer to the question. You would just say the function's continuous for all real numbers x, except where x is any integer. Or you could say except where x equals k, where k is any integer, or something along those lines. And then h of x has non-removable discontinuities at any integer value of x. So we just want to kind of specify that. I didn't state intervals here, although you could do something like this, negative 4 to negative 3, negative 3 to negative 2, just to kind of illustrate the pattern with a dot, dot, dot on either end. Like that could work as well. But I think in this situation, it would also be okay to just kind of say it in words as well. Okay, so then lastly, we were looking at the equation for sine of x. And for that one, really, it just kind of helps to picture the graph. And remember that this graph has no holes, no jumps, no asymptotes. It basically has no discontinuities. It's smooth and connected the whole way through. So it's continuous on the entire real number line from negative infinity to infinity. So in example 2, we're basically being given the same instructions. We're just trying to find values where f is not continuous and be able to classify them, and then also state the intervals where the function is continuous. And the function that we're looking at here is a piecewise function. So when you're looking at a piecewise function, the first thing I want you to look at are these domain restrictions and make sure that every x value is included there first. So we want to see, are there any values where x is not even defined? And it looks here like f of x is defined everywhere because I have all x's that are less than negative 2 and then all x's that are greater than and equal to negative 2. So every single x value is included. So I can check that off and say, okay, the function exists everywhere. That's the first thing you'd want to check. Then the next thing you'd want to check is, do those two sides come together and connect? So you'd want to check, does this y value equal the same thing as this y value right at the point where x is negative 2? Because that's where the function or the y value is changing from this expression to this expression. So first of all, f of -2, that's just the value of this piece when x is -2, right? Because that's the piece that includes -2. So we could just plug -2 into that equation just to see what f of -2 is. So it would be -4 plus 2, which is -2. So f of -2 itself equals -2. The y value is also -2. Okay. So I know that the limit as x approaches -2 from the right, that's also equal to -2 because this piece is also including values of x that are greater than -2, which would be on the right-hand side. So this and those are equal. Now what we need to do is make sure that this part that's on the left of -2 would also equal -2 when x is -2. So I would plug it in there, and I would get -6 plus 1. So it does not. It equals -5. So no, these two things are not equal. The limit from the left does not equal the limit from the right. So over here on the graph, if you want to take a look, on the left I can see as x is approaching -2 from the left, the y values are approaching -5. But on the right-hand side, as x approaches -2, the y values are also approaching -2. So what that creates in your graph is a jump, a non-removable discontinuity. So we know that that's what's going on in this particular equation. So the intervals where the function's continuous would be from -infinity to -2, and then again from -2 to infinity. So basically this part is perfectly fine, and then you jump over to this, and this part's perfectly fine. It's just right at -2 that we have the issue. So here's how I would want you to answer the question. You would say f of x is continuous for all x except x equals -2, because there is a non-removable discontinuity at x equals 2. So the intervals where the function is continuous would be -infinity to -2 and -2 to infinity. So let's look over here at another piecewise example. So again, I want you to first check, are there any values of x where the function's undefined? So I want you to check your domain restrictions first whenever you're looking at a piecewise function. So I notice in this piecewise function, neither one of these inequalities includes an equal sign. So what that means is that f of x is not defined when x is 1. It's defined for everything to the left of 1 and everything to the right of 1, but not at 1. So I notice that it could potentially be a removable discontinuity. But now what I need to do is check to see, oh, this should say 1. Sorry, that's a typo there. We want to check to see if these two pieces are coming together to connect when x is 1. So we know that f of 1 doesn't exist. F of 1 is undefined. But what we don't know is, does the limit exist? Does the two-sided limit exist as x approaches 1 from the left and right? So what I'm going to do is plug 1 into each piece. So I can see that on the left side, the values are approaching +1. And then on the right side, they are also approaching +1. So I can see over here in my graph, on the left side, the y values are approaching +1. And on the right side of 1, the y values are approaching +1. It just so happens that the function doesn't exist at x equals 1. So this is the part that doesn't work, right? The limit exists. These two are equal to each other, but there is no value for f of 1, so they don't equal that value because that value doesn't exist. So that would make this a removable discontinuity where the two-sided limit exists, but the value of the function does not. So the intervals where this function is continuous is everything to the left of 1, so -infinity to 1, and then to the right of 1. You would say f of x is continuous on the intervals from -infinity to 1, union 1 to infinity, period. So we answered the interval question and talked about where f was continuous, and then we would say there is a removable discontinuity at x equals 1. So we talked about where there was the discontinuity, what type it was, and the value of x where it occurred. So go ahead and take a look at this piecewise and see if you can come up with correct intervals where it's continuous and what type of discontinuities it might have. And then come back and check your answer with the video.
Okay, so with this piecewise function, the first thing, of course, I want you to check are the domains and making sure that f of x is defined everywhere. So I can see that f of x is equal to sine of 1 over x for every single x except 0. So that's every x with the exception of 0, and then it equals 2 at x equals 0. So it is defined for all x's, everything not 0, and then also at 0. So then what you want to do is see if the limit, the two-sided limit at x equals 0 exists. Does the limit as x approaches 0 from the right equal the limit as x approaches 0 from the left? And that both of those limits involve this piece, because this is what g of x equals for everything to the left and right of 0. So what I need to do is check the left and right-hand limits of this function when x is approaching 0. And what you might notice is that when you plug in 0 for x into the sine function, you end up with something that is undefined on the inside there. So then you can't really figure out what that limit equals. So it helps to take a look at the graph, either using Desmos or your graphing calculator. And so that's what this is here. This is the graph of sine of 1 over x. And you might notice that, I don't know if you can see, but x equals 0 is right there. And so the function this is one of those this is one of those rare cases where the function does not have a limit at 0 because the function is oscillating too much. It's bouncing back and forth between positive 1 and negative 1 so much, like it's just too much oscillation to the point where we cannot determine what that limit of sine would be at x equals 0. So coming back to our notes, we just would have to recognize that limit just doesn't exist because of oscillation on both the right and the left. That makes it a non-removable discontinuity since the limit doesn't exist. So the function's continuous everywhere else, though. If you look at the graph of sine of 1 over x, again, you can see it's nice and smooth along the graph everywhere up until 0, where we can't tell where it ends up. And then it's smooth to the right of 0. And then the value of 2 is obviously a solid point. So the function is really continuous everywhere else except 0. So from negative infinity to 0, and then also from 0 to positive infinity. It has that one non-removable discontinuity at x equals 0 due to the oscillation. So for our last example, it's a different type of continuity question, but a type you will most likely encounter on the AP test and also on our course test and final. So what it's asking you to do is say, okay, we're telling you that the function is continuous on the entire real number line. So there's no point of discontinuity. In order for that to be the case, we have to find the constant a or the constants a and b. Okay, so this is just a constant a1. These are the instructions from the book. In some cases, you have to find two constants. But in our example here, we just have this constant a right there. So figure out what the value of that would be in order to make the function continuous over the whole number line. So what we want to make happen is we want the limit as x approaches 0 from the right of the function to equal the limit as x approaches 0 from the left. And then it also needs to equal the value of the function when x is 0. Okay, so this is the piece when x is equal to 0. So what I'm going to do is plug 0 in for x, and I notice that that makes the 2x part go away. So this becomes a minus 0, which equals a. So I know that f of 0 is equal to a. So that is what both of these limits need to equal. So this part where x equals 0 is also the right-hand side. It would also be this limit. So I know that the value of the limit as x approaches 0 from the right of the function is this piece would equal a as x gets closer to 0. And I need that to equal the value of the limit of this function when x approaches 0 from the left. So I would need that to equal the value of the limit as x approaches 0 from the left of 4 times sine of x divided by x. So I don't know if you recognize this, but this is one of our special trig limits from an earlier section where we know that the limit as x approaches 0 of sine x divided by x is equal to 1. So if I were to sort of isolate this part of the limit, which I'm able to do, right, because we know the properties of limits too, says that if you have a constant, which in this case is 4 times a function, the limit would just be that constant times the limit of the function. So I know that the limit of sine x over x as x approaches 0 is 1. So 4 times that function would just equal 4 times that limit, which is equal to 4. So what I need is for the value of a to equal the value of this limit, which is 4. So a would need to equal 4. If it does, then as x approaches 0 from the left, this side goes to 4, and as x approaches 0 from the right, this side would also go to 4 if a were equal to 4. And also, when I plug 0 in here, and a is 4, I would just get f of 0 equals 4. So basically, I would make these three things all equal to each other by making a 4, and therefore the function would be continuous. Okay, so this next one, the u try, has two constants, a and b. So why don't you go ahead and try it, but then you can come back and check and see how to get the answer for this one. Okay, so for this piecewise function, there are two different values of x where the f of x values change, right? It goes from 3 to ax plus b to negative 3. So we have to make two conditions true in order for the function to be continuous on the entire real number line. So we need to make sure that the limit as x approaches 1 from the left equals the limit as x approaches 1 from the right equals f of 1. That would make f of x continuous at 1. And then we also need to make sure that the limit as x approaches 4 from the left equals the limit as x approaches 4 from the right equals f of 4. We need to make sure both of these continuity conditions are met for the function to be continuous everywhere. So for x approaching 1 from the left, we would have to look at this piece over here. So that limit would just be 3. Now the limit as x approaches 1 from the right would be this piece when I plug 1 in for x. So a times 1 plus b. And then f of 1 also ties into this first piece of 3. So the first thing that has to be true is that a plus b has to be 3. So we have that condition over here. But that only guarantees the function's continuous at 1. So then we have to also find the limit as x approaches 4 from the left. So that would be this part. So I'd plug in 4 for x, a times 4 plus b. That has to equal the limit as x approaches 4 from the right, which would be here, which is equal to negative 3. So these have to be equal. And then, of course, f of 4 is also negative 3 since that also goes with this piece. So we can see from here that 4a plus b has to equal negative 3. These two conditions have to both be true. So what that does is it creates a system of equations that you can then solve for both variables. So then you could also just do a quick little check to make sure that both of these things are true. So when x equals 1, if a is negative 2 and b is 5, I would have negative 2 times 1 plus 5, and that does equal 3. So then this part would be continuous because the limit as x approaches 1 of the function would equal 3, which is f of 1. And then when x equals 4, which would be negative 8 plus 5, which would be negative 3, then this part would also be continuous because the limit as x approaches 4 would also equal the value of f of 4, which is negative 3. So I can see that these would have to be the values of a and b. That concludes our lesson for 1.4. See you in class.